Let's suppose you want to purchase a painting and that you're scared of purchasing a fake painting. You can hire the services of a professional who knows exactly what a real painting looks like, such that when shown a fake painting, this professional can flag and say this is a fake painting, and when shown a real painting, the professional knows exactly that this is a real painting. Let's suppose for every fake painting, this professional publishes results or explains why the painting was flagged as fake. This means that this information has been made available to the individuals producing this fake painting. And once they have this information, they can then reuse that information to better produce these fake paintings. So let's suppose we have this painting, this original painting. Now, initially, they produce this kind of paintings. Clearly, the professional says that it's a fake one. And then they publish or explain why they say this is fake. Then the fake painting professionals reproduce this other painting, which now looks more like the originals. But then again, this professional flags this as a fake painting. Then we move on to this, and then finally to this. So we see clearly that as time goes on, this fake painting merchants actually have learned how to produce paintings which look like the originals. So at some point, the professional original painting recognizer doesn't even notice that this is a fake painting. So this is the principle behind generative adversarial neural networks, popularly known as GANs, wherein we have this generator model which takes a noise and then generates some fake data, and we have this discriminator or critic which knows how to classify an image whether it's real or fake. So in its output we have either 0 or 1. So this looks more like us having this distribution. Now we actually put this the distribution of the real data right here. We have this here. Then we have the distribution of the fake data. Obviously it's quite different from that of the real data. Then with time, as we keep on training this, what happens is this fake data now looks more like the real data distribution up to this point where they're quite similar. And then it happens that the critic or the discriminator no longer notices that these input images are fake. Now once we get to this point, that's the point of convergence of our GAN, then it means we could now just simply input any random noise here, and then we are able to generate this data or this fake data, which now looks like this original data. On this particular case, this original paintings. So talking about generating images or faces, all we do is we have many faces that have been put here as a real data, and then the generator tries to learn or tries to generate some fake faces, and then the discriminator is able to flag this as a fake one and this as a real one. And then with time, this now learns how to generate this fake faces which now look like the real faces. Here is the original GAN paper by Ian Goodfellow, Jean Bouquet, Merdy Mizar, Bingzu, David Ward, Shelgli, Ozai, Aaron Colville, and Yoshua Benjo. The proposed no framework for estimating generative models via an adversarial process in which we simultaneously train two models, a generative model G that captures a data distribution and a discriminative model D that estimates the probability that a sample came from the training data rather than from the G. The training procedure for G is to maximize the probability of D making a mistake. This framework corresponds to a mini-max two-player game. In the space of arbitrary functions G and D, a unique solution exists, with G recovering the training data distribution and D equal to half everywhere. That is, D is actually confused whether the input is a fake one or a real one. In the case where G and D are defined by multi-layer perceptrons, the entire system can be trained with back propagation. There is no need for any Markov chains or on-road approximate inference networks during either training or generation of samples. The exact model we shall be working with is the DC-GAN model. Here is a DC-GAN paper entitled Supervised or rather Unsupervised Representation Learning with Deep Convolutional Generative Adversarial Networks, hence the name DC-GAN. So we have DCGAN right here. This paper is by Alec Radford and Luke Metz with Sumit Shintala. They actually introduced a class of CNNs called Deep Convolutional Generative Adversarial Networks, DC-GANs, that have certain architectural constraints and demonstrate that they are a strong candidate for unsupervised learning. Training on various image data sets, they show convincing evidence that the deep or the DC-GANs learn a hierarchy of representations from object paths to scenes in both the generator and the discriminator. Additionally, they use the learned features for novel tasks, demonstrating their applicability as general image representation. Now let's look at the approach and the model architecture. Historical attempts to scale up GANs using CNNs to model images have been unsuccessful. This motivated the authors of the lab GAN to develop an alternative approach to it, iteratively upscale low-resolution generated images which can be modeled more reliably. They also encountered difficulties attempting to scale GANs using CNN architectures commonly used in the supervised literature. However, after extensive model exploration, they identified a family of architectures that resulted in stable training across a range of data sets and allowed for training higher resolution and deeper generative models. Core to the approach is adopting and modifying three recently demonstrated changes to CNN architectures. So here's a summary of this architecture guidelines for stable DC GANs. They replace any pooling layers with strided convolutions and fractional strided convolutions. So instead of using max pools or average pools, they used the strides or striding. They use batch num in both the generator and the discriminator. They remove fully connected hidden layers for deeper architectures. They use ReLU activation in generator for all layers except for the output, which uses the tanh activation function, and they use the leaky ReLU activation in the discriminator for all layers. Now the graphical model from the paper actually looks like this. We start with a noise, we then project and reshape. After this, we pass through several conv layers, and then finally we have this output of dimension 64 by 64 by 3. For our model, we should start by the generator. So right here we have the init size, which is the input dim divided by 4. We define this such that as we go through the network, we'll end up with an output dimension 64 by 64 by 3. In fact, an output dimension input dim by 3. The noise dimension is considered to be 128. We have this input. Then we pass the input. We have the dense layer, batch normalization, leaky ReLU, a reshape. Now, the aim of this reshape is so that we could be able to apply convolutions. Now, specifically, we shall apply the conv2D transpose as it permits us to upsample our features. We have the number of filters, we have the kernel size, we work with strides instead of doing max pooling. Then we follow this with another conv2D, but this time around stride 2. And we note that the role of the strides is actually for us to be able to multiply the height and width dimension by, in this case, for example, 2. So we follow this now with a batch normalization, like relu, and then conv2d. Note how the activation here is a tank activation as specified in the paper. So we run this, and there we go. We see clearly here how we live from the dense layer through the batch norm, like relu, and then with a reshape, we're able to get this. We upscale using the conv2d. This first conv2d doesn't upscale because the stride is 1. The next one upscales this value, so we live from 16 to 32, and then the next upscales the values from 32 to 64, while ensuring that the depth dimension is equals to 3. So now we have this ready for inputting in our discriminator. We now move to the discriminator model. For the discriminator model, we have this inputs. Here we have 64 by 64 by 3. The inputs could be real or it could be fake images. Then we have the pre-processing layer, which rescales our input images or our input fake images. Then we have the conv2d with stride 2. So again, yeah, we don't use the pooling layers to downscale. We have the another conv2d, and finally we have this dense layer because we are actually seeing whether the image is fake or not. Now let's run this. We'll see clearly how our discriminator model is formed.